as introduced, I'm Evann Smith. I'm a senior data scientist at Bechtel. I was going to lead in and say that Bechtel is probably the largest company you've never heard of, but I think Justin took care of that yesterday. Still, I'm going to reiterate a little bit about Bechtel before I start because I think it's important motivation for what we're trying to do here. So Bechtel is a 120-year-old company. It's privately held construction engineering project management. We have more than 50,000 employees. We've built over 25,000 projects on all 7 continents. And our industry is absolutely huge. So construction comprises about 13% of the world's GDP. McKinsey estimates that by 2030, it will be $13 trillion in spending. But we have a problem, which is that over the past 20 years, productivity has effectively flatlined. And this is not true for other industries. This is not true for other industries that are heavy in manual labor, like manufacturing, which has seen productivity double in the same time period. And this is really, really true with mega projects, which is what Bechtel does. 98% of mega projects overrun on time or cost. So the potential to optimize is really, really major here, and it's what we're trying to do. Bechtel's risen to the challenge by establishing the Big Data and Analytics Center of Excellence, where what we're trying to do is take 120 years of data, learn something from it, and optimize our processes. So Bechtel's BTech is a shared service where we try to identify what makes projects profitable, what makes them safe, what makes them high quality, and then be able to make better, faster, and smarter decisions. Of course, no one goes this alone. So we have 2 big partners here. The first is Miner and Cash, which is responsible for doing the pilot that established to Bechtel that this was something we should really pursue. They also set up our original team, a lot of the baseline architecture and engineering as well. And then our other partner here is Databricks. We made a strategic decision that we wanted to move into managed services so that we could focus on our high-value business problems, and data scientists like me don't need to pester an engineer every 30 seconds that I want to do something. So before we move into the details of the use case, I think it's worth asking what's unique about construction. And there are a few things. The first is that automation's not particularly common. And not only do we deal with a lot of manual processes, but many of them are resistant to easy automation. You can't, in fact, build a transnational rail line on an assembly line. Second, a lot of us in tech, I came from a startup, are used to agile development. We're used to iteratively improving our algorithms. But once you break ground on a construction project, it's effectively a waterfall process. You're not trying to iteratively build a bridge. It's a bad idea. And so what this means is that we're really trying to optimize the planning processes up front, which is the singular motivation for this use case. And we're really trying to invest now for rewards that we'll see some years in the future. And this is made incredibly more challenging for Bechtel because we build really, really, really big things. Justin went through a few of these. It's worth reiterating. You might have heard of the Hoover Dam, the Tunnel, Hong Kong International Airport, an entire city, which is the largest civil engineering project in the world today that we still work on. As well as most recently, 3 LNG plants for 3 different customers side by side on Curtis Island off the coast of Australia. So to state the obvious, right, these things are incredibly big, and there are millions of ways that you can build them. And more importantly, for someone like me as a data scientist, we observed that there was inconsistent productivity across similar parts of projects or across similar projects. And these things were built in different orders. Now, there's a lot of embedded knowledge at Bechtel over 120 years about how you might build these things, but there's also a lot of disagreement about what the best way is. And we simply can't go out and try everything. So our goal, which I'm going to talk about today, is to develop an artificial intelligence solution that can facilitate self-learning for the purpose of optimizing construction installation sequences upfront in the planning phase. We need to be able to provide valid erection sequences, including novel sequences that we have not observed or tried. We need to be able to simulate alternatives under various constraints and from various points in the installation process. We need to assist our planners in getting an initial understanding of a job and its constructability, but these projects also take years. So we need to assist in long-term planning and make sure that we can provide a detailed sequence that spans the entire duration of the project. So in this enterprise, there are three notable challenges that I want to touch on. The first is that while we have a lot of data, at the individual piece level, it's very unique. Many of our projects are wholly unique in their design, and there may only be a couple examples of a complete project, a complete installation that are directly comparable. This is our first challenge. Second is that we're operating in three-dimensional space, and there are many more possible sequences than there are constructible sequences. You don't want to hang the roof from a crane before you pour the foundation. And the third is that we operate with dynamic constraints. So we're talking about multi-year projects, which means a highly variable environment over the course of an entire installation sequence. And anything you do has the potential to have unforeseen knock-on effects, potentially years in the future. We need to be able to anticipate that and deal with it. So to address the data issue, we initially focus on pipe and steel, which are the two most important parts of our project, the guts of it all, if you will. And while there's a high degree of uniqueness at the individual piece level, we are able to generalize our inputs via clustering. And so we build types of pipe and steel, which is what we're working to sequence for installation. The second, to tackle three-dimensional space, which is where we're trying to install these components, we grid the world. So we cut up entire projects into 120-inch cubes, 10-foot cubes, and we can now characterize the landscape. And in particular, we're interested in characterizing how dense an area is, how much stuff gets installed there. Turns out the denser or more congested an area, the harder it is to install something into it. So in this representation, which is a representation of an actual area, the darker the red, the more dense the cube. Finally, we have the dynamic nature of installation, right? Years-long projects, unanticipated impacts. So this is where we draw from recent advances in reinforcement learning, and particular in strategic gameplay. But instead of a two-dimensional game board, we have a three-dimensional grid, where each space on the grid is characterized by its density. And instead of game pieces, we have individual pipes, or pieces of steel, each of which is characterized by its type. So that we can define a legal move in the game as one in which we install something that has not yet been installed into the space that, according to the engineering design, it's supposed to go. So what we're trying to do in this game is we're trying to minimize the total effort that it takes to complete an installation sequence. An effort here is defined by a function that we have learned from our empirical data across all of our projects. So then, in game structure, we can repeatedly play ourselves and try to beat our best score, try to minimize our effort over multiple games. All right, so how does this work? We can imagine an installation sequence as a tree, a decision tree, where each node is a possible move. And as you go down your installation sequence, you're descending this tree. So to choose a move and learn sequences, We use a combination of Monte Carlo tree search and a 3D convolutional neural net, which is a framework quite similar to the one used by AlphaGo Zero, though ours is a bit more complex because we're working in three-dimensional space. We have different types of spaces within that 3D area, and we have different types of pieces. We also recharacterize it as a single-player game. We're trying to beat ourselves. So in Monte Carlo tree search, briefly, we start at our given state, and we identify all possible moves. Then we want to predict their probabilities and simulate over them. So for one move, for one simulation, out of all the possibilities, we pick the most urgent move. And urgency here comes from a function that first privileges exploration, and then later asymptotically privileges exploitation of what we've learned. We play out to the end of a complete sequence. We predict whether that sequence would win, and then we back-propagate that through the tree. We do this over and over again for n simulations, 500 simulations in our tests here. And then we select the winningest next move. So that's one move. And we rinse and repeat, and we do this over the entire installation sequence. So to learn and predict the move probabilities and whether we're on a winning path, we use the CNN. So the CNN takes as an input a representation of the current installation state, your past several moves. We've experimented with everything from 2 moves to, say, your past 10 moves, as well as the remaining inventory that you have left to install. We start out with a convolutional layer, which has 64 filters, batch normalization, linear rectifier, the kind of standard architecture, followed by a series of residual layers, which uses a skip architecture. And then most importantly, this is a dual head. So we have a policy head that outputs an array of move probabilities that maps to our three-dimensional space. And then we have a value head that outputs a scalar, which predicts whether you've won or lost. So once you've completed a full sequence, full game's worth of Monte Carlo tree search, you can calculate the actual effort using this empirically defined effort function and go back and train your net. And what's really cool is that we have, in fact, not only learned sequences, but we've produced novel sequences. So this is a video Justin showed yesterday, but I want to show it again. On the left, we have the original as installed in the real world sequence. On the right, we'll have a novel sequence that we learned. This has never actually occurred in the world, but our data tells us that it should be more efficient. And what you'll notice is that on the left, in the original sequence, you see the horizontal stuff installed first, then you get the vertical stuff, then you get the little stuff at the end. What happens in the novel sequence is we work from the center out. And the sequence really works to minimize the degree to which you're trying to install stuff in tight spaces. So I have my mouse. And the sequence on the right is, in fact, a bit faster. So this is phenomenally cool, and we're very proud of this. But it's also really slow and computationally complex. By way of comparison, someone estimated that to reproduce AlphaGo on commercially available hardware, which again is a simpler game, would take 1,700 years. DeepMind spent about 25 million on hardware alone for AlphaGo Zero. So how can we do this smarter? And this brings us to the part where we go through the iterative engineering. And this is where Databricks really came through for us. How do we get from this algorithm, which is really powerful, to something that can actually produce actionable insights that can be applied to projects in the field? Or, put differently, how do we make this work in the wild? So we started with a relatively basic Spark paradigm. We have our driver, we have our workers. Our first thought was that we could parallelize the simulations. So here, what we do, we initialize our net on the driver, send it over to the workers, expand our moves, select the most urgent moves, send them back, predict our installation values, back propagate, so on and so forth. Move this through this cycle, and then once we get a complete sequence, train the net. Sounds great, but we can't do it. And the reason that we can't do it is that our simulations are sequentially dependent. They're in fact not embarrassingly parallelizable. Because remember, the urgency equation that we use to decide what move to pick next needs to balance exploration with exploitation. That means we need to know what we did before. So that means our workers need to simulate a complete installation. We need to run many simulations. We need to have a complete game occur. Looks like it gives us a simpler picture. We have our driver, extract the weights. But what this means is that we're now demanding a lot more of our workers. They need to be able to access the net because they need to be able to make predictions over the course of simulations. So with this complete cycle then, that means we end up with model parallelism. Most AI solutions out of the box are built to handle data parallelism. Model parallelism is much harder, and we have a really, really big neural net. So to tackle this problem, we started harassing Databricks. And the first thing we tried to do was improve our net performance in terms of prediction and training over GPUs. Start out with Keras, using the multi-GPU setting, got us nearly linear speed up for 8 GPU cores. It's a pretty good start. But it wasn't fast enough. We were still struggling. So we went back to Databricks, and the ML runtime that they announced yesterday, they built us a custom image, and we unleashed that and started employing Horovod. So now we can distribute our net across multiple GPU machines. Get a lot faster. But we're still too slow. And we're still too slow fundamentally because of the simulation issue, which is that they're sequentially dependent. And Spark, in this paradigm, uses primarily synchronous communication. So that means we're constantly waiting. We have to wait for all of our games to complete before we can come back and train our net. So again, we went back to Databricks. And they built us the ability to stand up custom clusters. So now, we have a multiple GPU cluster where each node can operate independently. And we're able to employ the MPI that underpins Horovod to do asynchronous communication between these nodes. So our structure now looks like this, where we have our network trainer, and then we have a series of simulators. And they're operating in something like perpetual motion. So from our net, we extract our weights, we send them over. Our simulators pick it up, they have copies of the net, they set the weights. They run through a game. Upon completing a game and completing a sequence, they send that sequence, as well as the effort values, the outputs, back, and we train our net. Every time we train the net, we re-extract the weights, we reset them, and we're in this consistent iterative cycle. And it's helped. So in the initial implementation, this is for the smallest area of a plant. I'm going to say ballpark 70 pieces of pipe. With 500 simulations per move to get to 1,000 games. When we kicked it off, we were looking at about 10 plus days. With the GPU accelerated net, the Horovod implementation, we're able to get down to a little over 2 days. And then with asynchronous communication, we're now running this in about half a day. So it's an impressive speed up. It's still too slow. It's still the smallest part of the plant. And we're continuing to work on it. We're continuing to try to improve both the algorithm in terms of generalizing the input space. I'm also very excited to get home and unleash this on P3s, which we have not tried yet. And I'm hoping that we'll get some gains there. We're also working on figuring out how to deliver these results to the field, embed them in the work packages that our planners use on site, on projects, and ultimately improve our productivity. The goal is to take the 100 years of embedded knowledge that Bechtel has and pair it with this cutting-edge architecture and deep learning to really drive the industry forward. All right, doing well on time. So I just want to touch before I close for questions on some of the other cool stuff that we're doing that we have in the pipeline. We're working to monitor real-time engineering performance, improve estimation accuracy and proposal outcomes, as well as look at our employee career development. And what's really phenomenal about all of this is that it's new, right? This is a huge industry, 13% of the GDP. We're building things that last lifetimes, and we've never done any of this before. So if we're able to pull it off and do something truly innovative, we believe that these algorithms can fundamentally disrupt the way that we build things going forward. And we're very excited about that. So with that, we've got about 5 minutes left, so I'll close and take questions.
So I'd like to begin by saying, this is a super cool project, and I don't think I've ever seen anything like it before. I guess my primary question is, how applicable is this actually to construction? So you have this really cool RL algorithm that can automatically plan pipes for you, but have you actually tried putting something like this into practice? And if you haven't yet, at what point in time do you think it would be possible to do something like this practically?
Yeah, so we haven't unleashed it in the wild yet, right? We're still trying to make it to run quickly enough, though. But we are working with SMEs on particular projects that, in fact, are moving to a new phase of construction in about September. And we're working to have sequences that can be validated in the field. So in the next couple months, we're driving there. We're already producing sequences, working on visualizing them in the way that you saw in the video so that we can share them with our experts and planners and make sure we really are learning constructible things. So the answer is that we're driving there, and the goal for which we believe will succeed is this September, to have constructible sequences in the field. Once those are validated, then we'll worry about building out a tool that can be used in the planning process when the engineers sit down and do this.
Hi, sorry if I missed something, but my question is, what the advantage of using this approach against, instead of using something more traditional like optimization, constraint programming, job shop scheduling, things that kind of built for sequencing?
Yeah, absolutely. So there are a few advantages here. The one that I think is most compelling is the ability to learn novel sequences, which is, we really can't try the millions of ways that you can construct these things. We may only have a few complete examples in the real world, and so we need a way to work through possible new ways of building things. And I think that's the real advantage of this approach. It also, by working through the CNN, allows us to actively represent that three-dimensional space that we're trying to install things into.
Just curious about your data transformation process. How did you take all that historical data so you can feed it into this beast?
Well, the man you should really speak to is the one sitting right there behind you, Niels Cash. So we worked from 3D models of plants, which Niels did a spectacular job gridding and creating that, that cubed representation that you saw in the presentation. And then we also have all the records from our sites. When our workers install something, they in fact have to claim credit. They have to say when they've taken it from the laydown yard to staging, when it's been put into place, when it's been welded, when it's been tested, when it's complete. And so we have, for each individual piece number, we have all that historical installation data. Yeah, exactly. Yep, for sure.
Any other questions? If not, thank you, Evan.